All right, so I want to continue our discussion of the Brock Mirman model, the optimal stochastic growth model. Today, what I would like to accomplish is to finish talking about some of the basic assumptions that need to hold in order to establish the existence and uniqueness of the Bellman equation or whatnot. We started talking about that at the end of the class last period. I'm going to touch on just a few more, but the main two things I want to accomplish today are to prove proposition 2, I believe, which is on some important properties about the policy function. And then I'm going to kind of skip ahead a little bit and go to the canonical version of the Brock Mirman model and show how to set that up and solve that analytically for the policy function. Things are very similar, but in a few ways slightly different than the treatment of the growth model with no uncertainty. And then what we will do next Monday then is backtrack a little bit and talk about the long run behavior of the Brock Mirman model. That is characterizing this kind of transition towards a limiting invariant distribution as opposed to a steady state. So I'm thinking 2 more days on this topic and we will be finished. Okay, so here is the statement of the general version of the Brock Mirman model as we discussed it in the last class. And it's given in recursive form. Right, so we've got the value function is equal to the maximum over choice of the policy function, K prime, of current utility plus discounted continuation return. That is next period's expected value function. And here is the constraint correspondence, okay? Now in the last class, we sort of verified that the state variable capital has to reside on a compact set. We showed that. We also showed that the constraint set is compact valued and continuous valued and non-empty. We showed that the expected lifetime utility function exists and is finite, and that basically that result comes from the fact that since the capital stock and the random variable z live on a compact set and that the utility function is continuous, then the utility function will be bounded every period, right? Which is going to put an upper bound on what expected lifetime utility can be. So the lifetime utility exists and is finite. So there's something there that the planner can choose from, a non-empty constraint set, and there's some well-defined objective that the planner can maximize. This ensures the existence and uniqueness of the value function, that is of the Bellman equation. A few other assumptions are needed to establish the strict concavity of the value function with respect to K, which was important because that enables us to ensure that the sequence of state contingent plans that maximize the planner's problem is unique, right? And can be represented as a time invariant policy function. Now, what were those assumptions? One, that the period payoff function had to be concave, strictly concave in the capital stock, right? That is, if you take 2 points, let's say K1 and K2, that the utility evaluated at the linear combination of those 2 points has to exceed the linear combination of utilities evaluated at those 2 points distinctly, right? We don't need to go through that exercise again because it's the exact same thing. We just have to accommodate the utility function to account for the stochastic variable z. The other assumption that was needed was the convexity of the constraint correspondence, which says that the linear combination of 2 points, let's say K prime 1 and K prime 2, has to live inside of the constraint correspondence determined by the linear combination of the 2 points K1 and K2, right? Again, that exercise that we've already done in the deterministic world is equivalent here. I don't know why it keeps doing this. What else? We also showed that in order to demonstrate that the value function is increasing in the capital stock, that the utility function has to be increasing in the capital stock for a given K prime, right? Well, that's obvious. If K is bigger, then production is going to be bigger, and therefore consumption is going to be larger, and utility is increasing in consumption, right? And so the value function will be increasing in K as well. And by the way, that also requires that G be monotone. You guys remember what that is? Yeah. That's if a K2 is bigger than a K1, then the constraint set defined by G of K2 fully contains the constraint set defined by G of K1. Right? Again, I don't want to have to go through all of that stuff. The only thing that is really new here that I think we should quickly kind of verify, because we will need it to go through the proof of proposition 2 today, is the contents that are part of assumption 6 regarding the behavior of Z. Remember, there were 3 parts of that assumption. One was that G needs to be monotone in the random variable Z. The utility function needs to be increasing in Z. And then that the random variable Z itself needs to follow a monotone Markov process. Well, the third one there is true by assumption. We've assumed from the get-go that Z follows a monotone Markov process. Do you guys remember what that means? If Z follows a monotone Markov process, then that means for any non-decreasing function f, that is, it's non-decreasing in Z, the expected value of f of Z prime conditional on Z is also non-decreasing in Z. We'll use that today. We're going to assume that Z follows a Markov monotone process. But what about the first 2 parts of that assumption? One was that the constraint correspondence G is monotone in Z. Well, we can demonstrate that fairly easily. Let's take a Zi less than Zj, right? And that's because index I is less than J. Remember, we've written these in ascending order in the set capital Z. Well, what is G of K Zi equal to? That's the interval 0, closed interval 0 to f of K Zi plus 1 minus delta K. Well, you'll notice that since f is increasing in Z, that's fully contained in the set 0 f of K Zj plus 1 minus delta K, which of course is just equal to G of K Zj. And that, again, it's because f is increasing in Z. That was an assumption we made in the last class. Higher levels of the productivity shock increase output for a given amount of capital. So indeed, G is monotone in Z as it is monotone in K. The other assumption, or the other component of assumption 6, that is that the period utility function has to be increasing in Z. Well, again, that's straightforward, right? For exactly the same reason we described above. U of f of K Zi plus 1 minus delta K minus K prime has to be less than U of f of K Zj plus 1 minus delta K minus K prime for all K and K prime in 0 to K hat, where K hat is that highest possible value that capital can take in this world that we characterized in the last class. And the reason why that's true is because f is increasing in z. And if f is increasing in z, then as z gets bigger, f gets bigger, but that means that consumption gets bigger. And we know that u is increasing in consumption. So the payoff function is also increasing in the technology shock. Higher values of the productivity disturbance increase both the production function as well as utility. And so the constraint correspondence is monotone with respect to z. Okay, you guys have any questions? That really, I mean, this is not really a formal proof. We were just kind of sketching what we would do to prove proposition 1. But showing a lot of those assumptions is exactly the same as what we did earlier in the semester. Okay. All right, this leads me to proposition 2, which is really the main thing I want to talk about today. In the Brock Mirman model, the policy function for next period's capital stock, written as pi of kz, is strictly increasing in both of its arguments. Policy function is strictly increasing in both of its arguments. We will need to establish this in order to determine what the long-run behavior of the Brock Mirman model looks like next week. Okay, how can we actually prove this? Well, let's take the capital stock first. We're going to do one thing at a time here. Let's prove that the policy function is increasing in the capital stock. And then we'll do with respect to z. In other words, if we increase the state of the amount of capital we have at the beginning of this period, then our choice for next period's optimal value of capital is going to be higher. That's what we're saying here. Okay. Because the payoff function is differentiable by assumption, and because the unique value function up here is also differentiable by assumption, then we can, and strictly concave, then the first order condition is both necessary and sufficient to characterize the optimal policy function, right? What is that first order condition? If we were to imagine taking the first order condition of this Bellman equation and we evaluate it at the optimal policy function, what do we get? It's negative u prime f k z plus 1 minus delta k minus k prime star, right? The negative comes from the chain rule there, plus beta times the expected value of, let's see, v sub k, so the derivative of the value function with respect to capital, evaluated at k prime star z prime, conditional on z, would be equal to 0. Now, of course, k prime star, because there is a unique solution to this problem, can be represented as this policy function, pi of kz. If we plug this into the first order condition, we get u prime f of kz plus 1 minus delta k minus pi of kz is equal to beta times the expected value v sub k times k prime star is pi of kz comma z prime conditional on z. This must be true for all z. This looks to me, since the value function is differentiable, utility is differentiable, and the policy function is differentiable, looks to me like we can take the derivative of this condition with respect to the existing stock of capital K to try to determine the sign of the derivative of pi with respect to K, right? So let's differentiate this condition with respect to K. In other words, do something that looks kind of like the implicit function theorem here. Well, we would get U double prime, and I'm just going to be lazy here and call this C, consumption, times what? Well, where does K end up in this expression? You would have an F sub K, that is marginal product of capital, plus 1 minus delta minus pi sub K is equal to beta times the expected value of, let's see, the derivative of V sub K with respect to the first argument, chain rule, times the derivative of pi with respect to K, conditional on Z. What I want to do here is group these terms that depend on the derivative of pi with respect to K. So I'm going to be left with a U double prime of C, and I'll call this C star just to understand that it's the optimal value of consumption, times the marginal product of capital plus 1 minus delta is going to be equal to, let's factor out a pi sub K from the term that is left over, and we can factor it out of the conditional expectation because you'll notice here it doesn't depend on Z prime, right? We know what pi sub K is after having observed Z, so we can pull it out of the conditional expectation. Times, let's see, U double prime of C star plus a beta times the expected value of V KK pi of KZ Z prime conditional on Z. You guys see how I did that? So we can essentially solve this equation for the derivative of pi with respect to K. Well, it's easy to sign. What's the sign of U double prime? It's negative. Utility is strictly concave. What is the sign of this thing in squirrely brackets here? Marginal product of capital plus 1 minus delta. That's a positive plus 1 minus a positive fraction, so that's a positive. The sign of U double prime is negative, plus what is beta expected V sub KK? Is that positive or negative? The value function is strictly concave, meaning that the second derivative of the value function with respect to K is going to be negative. So we've got, it looks to me like on the left-hand side, we've got a negative times a positive is a negative is equal to the thing we're looking for times a negative plus a negative is a negative. And so that looks to me like then that the derivative of pi with respect to K then has to be greater than 0. That makes sense? Okay. Now, the second part of proposition 2 is to show that pi of K Zi is indeed going to be less than pi of K Zj for all K in 0 to K hat when Zi is less than zj. We want to show that the policy function is also increasing in the random productivity shock, z. As z increases, the optimal choice of next period's capital is also going to go up. Now, how do we do that? If z was a continuous random variable, we might be able to appeal to derivatives like we did in the first part of this proof, right? But it's not, it's a discrete random variable. So I'm going to do this more or less by contradiction. Okay, let's assume here that I is less than j. All right, we're going to take an I that's less than j. And so zi is less than zj. Remember, we've ordered these z's in the set in ascending order. Let us suppose that pi of k zi is not less than pi of k zj, but is actually greater than or equal to pi of k zj. In other words, I'm gonna suppose here that the result we're looking for is exactly the opposite, that the higher z gets, the lower the policy function gets. All right, so pi of zj is less than or equal to pi of zk. And again, that's for all k on its feasibility set. Can I do a proof by contradiction here? Okay. We know from the first proposition that we talked about in the last class and at the beginning of class today, as well as, I guess, one of the earlier theorems regarding stochastic control problems, that the value function v is strictly concave, right? So if pi of k zi is assumed to be bigger than pi of k zj, then that implies that the derivative of the value function with respect to k evaluated at pi of k zi, comma, let's say z prime, should be less than or equal to the derivative of the value function evaluated at pi of k zj, comma, z prime. And that's for all z prime on big Z. You guys see what I did there? The value function is strictly concave. So if I've assumed that pi of zj is less than or equal to pi of zi, then that means the slope of the value function evaluated at that point is actually bigger than or equal to the slope of the value function evaluated at pi of zi, because v is strictly concave, just like the production function and the utility function. Okay, in other words, what have I just demonstrated here? I've demonstrated that the function v of v sub k itself, so v sub k is non-decreasing in z. It's a non-decreasing function of z, right? Think about it. I've got zi less than zj. And what follows is that the partial derivative of v with respect to k evaluated at zi is less than or equal to the same function evaluated at zj. So my supposition here leads me to the conclusion that the slope of the value function is a non-decreasing function in z. Now, why is that important? Remember, z follows a monotone Markov process, right? So if the function v sub k is non-decreasing, then what else must be non-decreasing? It follows then that the conditional expectation of v sub k evaluated at pi of k zi conditional on zi must also be less than or equal to the conditional expectation of v sub k evaluated at pi of k zj comma z prime conditional on z. You guys follow that? So I've established that the derivative of the value function with respect to k is a non-decreasing function in z. And that follows from my supposition. Because we have assumed that z follows a monotone Markov process, then that means the conditional expectation of v sub k must also be a non-decreasing function of z. So zi less than zj means that the conditional expectation of this object conditional on zi is less than or equal to the expectation of the same object conditional on zj. See that? Okay. If I multiply both of these guys by the discount factor, that doesn't change the conditional expectation, right? Now, do you guys see where I'm going with this? If beta times the conditional expectation of this object evaluated at zi is less than or equal to beta times the conditional expectation of the same object evaluated at zj, then that implies that the marginal utility of consumption evaluated at f of k zi plus 1 minus delta k minus pi of k zi has to be less than or equal to the marginal utility of consumption evaluated at f of k zj plus 1 minus delta k minus pi of k zj. What do these discounted conditional expectations terms equal? They equal these marginal utility terms from the first order condition of the Bellman equation, correct? So if this is less than this, then that means u prime evaluated at zi is less than or equal to u prime evaluated at zj. That follows from the Euler equation. Now we're getting somewhere. If u prime evaluated at zi is less than or equal to u prime evaluated at zj, then what do we know about the relative sizes of the terms inside the utility function? Utility function is strictly concave. So this is going to imply then that what's in the utility function here has to be bigger than what's over here, right? So f of k zi plus 1 minus delta k minus pi of k zi has to be bigger than or equal to f of k zj plus 1 minus delta k minus pi k zj. And that's because u double prime is negative. This cancels with this. And therefore, f of k zi minus f of k zj is bigger than or equal to pi of k zi minus pi of k zj. What's the sign of this term? F evaluated at zi minus f evaluated at zj. Zi is assumed to be less than zj, correct? So f evaluated at zi is less than f evaluated at zj. This whole thing is negative, right? Therefore, what do we have? We have pi of k zi minus pi of k zj has to be less than or equal to 0. And so pi of k zi has to be less than or equal to, not less than or equal to, it's going to be strictly less than, right? Because this is going to be strictly negative. So pi of k zi is less than pi of k zj. And that violates our supposition. We started this argument by assuming what? That pi of k zi is greater than or equal to pi of k zj. It follows directly from that the exact opposite. So it must be the case then that if zi is less than zj, pi of k zi must also be less than pi of k zj for any feasible value of k. So indeed, the policy function is not only increasing in k, it's also increasing in the technology shock z. Okay, you guys have any questions about that? Let us now characterize let's derive a full statement of the equilibrium of this model, just to be formal about how to characterize the solution. Okay, again, here is the recursive representation of the Brock Mirman model that we stated earlier. What I want to do is derive the full kind of, I don't want to call it a competitive equilibrium because this is a social planner problem, but let's write the sequence of equations using discrete time notation that fully characterizes the equilibrium of this model. Okay, to do that, what do? First, we derive the stochastic Euler equation, and we couple that with the transversality condition, right? So what are the steps in finding the stochastic Euler equations? One is the first order condition of the Bellman equation. That's going to give me negative u prime of c plus beta times the expected value of v sub k, k prime z prime conditional on z is equal to 0. That must hold at the optimal choice for k prime. In order to derive these stochastic Euler equations, we have to, of course, get rid of these value function terms by appealing to the envelope condition. The derivative of the value function with respect to the capital stock is going to be u prime times the marginal product of capital plus 1 minus delta. Recognizing then that optimal capital can be expressed as a time invariant policy function, pi of kz. We can scroll the envelope condition forward 1 period and use that expression to substitute it into the first order condition to derive the set of stochastic Euler equations, which should look like the following. U prime f of kz plus 1 minus delta k minus pi of kz is going to be equal to beta times the expected value of v sub k scrolled one period ahead. So that would be u prime of f of, let's see, pi of kz comma z prime plus 1 minus delta pi of kz minus k double prime. So that would be pi of kz comma z prime times the marginal product of capital next period, which would be f sub k, evaluated at pi of kz comma z prime plus 1 minus delta. All of that conditional on z. That must hold for any possible value of z. Hence, we have really a system of stochastic Euler equations, one that must hold at all dates and in all states of nature. We've transformed the first order condition from a functional equation in V into a functional equation over the time invariant policy function. And the objective then would be in a problem that can be solved analytically is to find an analytical expression for that policy function. Now, if I want to write this stochastic Euler equation or these stochastic Euler equations in a form that is more congruent with time subscripts, that looks a lot nicer, but recognizing that the values of these variables are the optimal ones, then how do I do that? This first one here would be u prime of what? This is just the optimal value of consumption, right? Is equal to beta times the expected value conditional on date t information of what? U prime, that's just optimal value consumption at date t plus 1, right? Times the marginal product of capital at date t plus 1 minus delta. This is the stochastic intertemporal Euler equation that must hold for all dates t and all possible realizations of the shock z, where the expectation is conditional on information that is known at the beginning of date t, that is whatever the realization of the shock is. Since I'm carrying around consumption terms in my statement of equilibrium, I'm obviously going to need to also include the resource constraint. So consumption is equal to f of kt zt plus 1 minus delta kt minus kt plus 1. An equilibrium in the Brock Mirman model is a sequence of consumption and capital that satisfies these two conditions for all time t for some given initial value of capital, and what? And also that the sequence has to satisfy the transversality condition. What is the transversality condition in this problem? Can you guys write it down? Well, we know it starts with a limit as t approaches infinity of what? Not the discounted marginal utility value of the state, but the conditional expected discounted. So it's the expected value conditional on date 0 information of the discounted value of the marginal utility value of the state. So u prime of ct f sub k kt zt plus 1 minus delta times KT is equal to 0. The optimal sequence of capital stocks and consumption, C stars and K stars, must satisfy the first two equations every single period, but must also satisfy the transversality condition in the long run. That is, it must generate allocations that are equivalent or will respect the lifetime budget constraint in an Arrow-Debreu competitive environment. The optimal policy functions that come out of this problem will satisfy these equations over time. Okay, you guys have any questions then about that? I'm on the statement of equilibrium in this model. All right, like I said before, I'm going to skip ahead to, I believe this is section 1.5 in the notes, to provide a little bit more intuition on this before we talk about the long run behavior. This whole idea of the Brock Mirman model not converging to a steady state, but rather converging to what we call a limiting invariant distribution for the capital stock and consumption is a new concept. Let me put that off until next Monday and work through just the canonical example first, because this is the one in which we can find an analytical solution to these policy functions that have to satisfy the equations just written down. All right, so first things first, what is the canonical Brock Mirman model? The planner chooses sequences of capital and consumption over time to maximize the conditional expected value of lifetime utility of the representative agent, where the representative agent's period utility function is given by the log of consumption. And the thing that constrains the planner is the period by period resource constraint, which says that capital for next period has to be equal to output from this period, which is Z times the production function, which we're going to assume is Cobb-Douglas, minus whatever we consume. So here we're assuming that every period the capital stock fully depreciates. So delta is equal to 1, utility is logarithmic, and production is Cobb-Douglas. Consumption, of course, has to be greater than or equal to 0. The capital stock is constrained to be greater than or equal to 0. Initial capital is known. And what else is known? The planner also knows what all the possible values the random variable Z can take in any given period. And it also understands fully the probability distribution from where those random shocks are pulled. In particular, it's a first order Markov process where the probability distribution can be characterized with the transition matrix Q, where the element Qij of that matrix is given by the probability then that Zt is equal to Zj, conditional on Zt minus 1 being equal to Zi, right? This is more or less the full statement of the model. Okay, this is the sequence problem. The planner wants to write down the Bellman equation. You guys know how to do that. It's going to be the value function defined over this augmented state, K and Z, would be equal to the max of K prime over the constraint correspondence, which is given by the closed interval between 0 and the maximum amount of capital that can be carried into next period would be Z times K to the alpha, since the depreciation rate is 1. The Bellman equation is given by the optimal current return, which is the log of consumption, or alternatively, Z times K to the alpha minus K prime, plus the discounted expected value of the continuation return, v of k prime z prime, conditional on z. And that is true for all z in big Z. We've already verified that the assumptions that are needed to establish the equivalency between these two problems are going to hold. So the solution to the Bellman equation will correspond to the solution to the sequence problem. All that stuff holds. So what we're looking for here is a solution for the policy function, which shows how the optimal value of next period's capital depends on today's capital as well as the realization of the technology shock. Now, the method that we have used to solve these types of problems is a guess and verify strategy. There's several ways of going about this. Your all's tests indicated, by the way, I have your tests. I forgot to give those back to you, didn't I? I'll give those back to you before I leave. You did very well with them, so there's no need to worry. I think I brought them. I know I graded them. There's a variety of ways to solve these problems. They're all using a guess and verify strategy, but you can either guess a policy function and use a matching coefficients strategy to determine the unknown coefficients, or you can guess the value function directly. I was kind of surprised that you guys took a variety of different methods to doing that. Not all of you just simply guessed the policy function. Some of you guessed the value function. What I'll do is I'll guess the policy function, and then I'll let you guys go and do the value function guess method on your own. Okay, all of them should result in the same answer. Okay, so let's solve this problem. If we take the first order condition of the Bellman equation, we're going to get what? Negative 1 over z k to the alpha minus k prime plus beta times the expected value of v sub k, k prime, z prime, conditional on z, is equal to 0. So the optimal choice of k prime must satisfy the first order condition. To employ this method, we have to get rid of the value function term. And so we need to take an envelope condition, right? So v sub k would be equal to, what is that? Alpha z k to the alpha minus 1 divided by z k to the alpha minus k prime star. The envelope condition must be evaluated at the optimal value of the control. We then can scroll the envelope condition forward one period and insert it back into the first order equation to obtain 1 divided by z k to the alpha minus k prime star is equal to beta times the expected value of, let's see, what would that be equal to? That's alpha z prime k prime to the alpha minus 1 divided by z prime k prime to the alpha minus k double prime, the optimal value of capital 2 periods from now, conditional on the current realization of the shock. I think I wrote that down right. And this must hold for all z. So these are the stochastic Euler equations. All right, now what do we want to do? We want to conjecture that the optimal policy function takes a particular form. Anybody have any guess what that form should look like?
Z times k to the alpha.
Sorry?
A times z times k to the alpha.
Yeah, it's going to look like the production function, which is z times k to the alpha with some constant attached to it. So let's call that a times z k to the alpha. All right, this is our conjecture. let's plug that guess back into our stochastic Euler equations. And what are we going to get? 1 divided by zk to the alpha minus k prime, well, that's a zk to the alpha, is equal to beta times the expected value of alpha z prime, let's see, k prime to the alpha minus 1. Well, that's a z k to the alpha quantity to the alpha minus 1 divided by z prime k prime to the alpha. So that's a z k to the alpha raised to the alpha minus k double prime. Well, that is an a z prime times k prime to the alpha, right? You guys see that? K double prime would be a z prime k prime to the alpha. Well, k prime to the alpha is, of course, just a z k to the alpha. Again, all of this conditional on z. Okay, so things are a little different here. It looks very similar to the deterministic case, right? But what's the main difference is that on the right-hand side, we have this conditional expectations operator, okay? Let me just assume, without loss of generality, okay, that the current value of z is just zi. It doesn't matter what you choose. It could be z1, z2, zn. Let's just take it for zi. Then what does this expression look like? It's going to be 1 divided by, let's see, zi k to the alpha minus a zi k to the alpha. So that's a 1 minus a times zi k to the alpha. What does the right-hand side look like? Well, that's beta times an expected value of something that depends on z prime. Now follow me here. We know what the current value of z is. It's zi. But there's a bunch of z primes here. That's tomorrow's or next period's value of the shock, which we don't know. But we do know what its conditional distribution is. We know what it could be and what the likelihood of each of those possible zj's are in the next period, given that we know that z is equal to zi today. So how do we evaluate this conditional expectation? You take the sum over all possible values of j from 1 to n of the weighted average of each possible event weighted by the probability of transitioning to that state. In other words, it would be qij times this object inside for every possible value of z prime. So that would be alpha, let's say zj, a zi k to the alpha raised to the alpha minus 1 over zj, a zi k to the alpha raised to the alpha minus a zj times a zi k to the alpha raised to the alpha. Okay, let me stop there. You guys see what I did? So there are capital N possible values that z prime can take. Okay, that's the z in the next period. I want to evaluate the expectation of this term. The reason why it's random is because it depends on z prime, which we don't know what it's going to be, but we know what it could be. And we know the probability of moving from state I to state j. That's the transition matrix. So we evaluate this conditional expectation by weighting each of these possible zj's from 1 to n over each of their transition probabilities. now we're getting somewhere, right? A lot of this stuff cancels. ZJ, ZJ, ZJ cancels. An AZI k to the alpha raised to the alpha cancels here, here, and here. And so this becomes beta times the sum from j is equal to 1 to n of qij times, let's see, this is an alpha over a 1 minus a times, there is a AZI k to the alpha, all of that raised to the negative 1 left over. You guys see that? So these terms cancel and you're left with this discounted sum then of these transition probabilities times the thing that's left over after I've made these cancels is alpha divided by 1 minus a times an AZI k to the alpha inverse. Now look, this term here, in fact, this whole term here does not depend on j in any way, correct? So you can pull it all the way out of the sum. And so you're left with then, let's say, an alpha beta over 1 minus a times a 1 over a zi k to the alpha times the sum from j is equal to 1 to n of qij. You guys follow? Okay. Other stuff cancels. Here's a 1 minus a. Here's a 1 minus a. Here is a zi k to the alpha. Here is a zi k to the alpha. What's the sum from j is equal to 1 to n of qij equal to?
N times divided.
Nope. It's equal to 1,
Oh,
right?
yeah.
That's just the sum of all the transition probabilities. And so what are we left with? We're left with A is equal to alpha beta. Ta-da. Which is exactly the same policy function we saw in the deterministic growth model. And that should not be surprising because really the only difference is we've added a linear productivity shock to the production function. And so kt plus 1 then is going to be equal to alpha beta zt kt to the alpha. Ct would simply be equal to 1 minus alpha beta zt kt to the alpha. Okay, questions about that one?
But how did that sum go to 1?
It has to. What's the, if you add the probability, if you start in zi, what's the probability that,
It's all of them.
yeah, it's every possibility, right? What's the probability that you're going to flip heads and or tails in the next time you flip a coin? It's equal to 1, right? You sum up all the possibilities of where z could transition to, it has to be equal to 1. Okay, I've got about 15 minutes left, so let me spend a little bit of time talking about how we can actually solve for the value function here. Again, there is one element of this, excuse me, that is a little different than what we saw in the deterministic world. Now remember, the value function is basically equal to the optimal value of the current return, which was zk to the alpha, minus the optimal value of the current return, which is the log of zk to the alpha minus k prime, which is pi of kz, plus the discounted expected value of the continuation return, which is v of pi of kz, z prime conditional on z. What I'd like to do is actually derive an analytical solution to the value function. That's going to require that we make a guess of what the value function looks like. Any ideas on what that guess should, what form it should take? The guess of the policy function should look like what's in the resource constraint, that is the production function. The guess of the value function should take the same shape as the utility function. It should be logarithmic, okay? But here we have two state variables, not one, right? We have capital, but we also have technology. So the value function, a good guess of the value function might be constant A plus some constant B times the log of K, plus let's say some constant C, don't confuse this with consumption, times the log of Z. Let's try this one. Okay, how do we determine these unknown coefficients then, A, B, and C? Well, the value function, that is A plus B log K plus C log Z, should be equal to the maximized value of the right-hand side of the Bellman equation, which was the log of zk to the alpha minus, what's the policy function that we found in the last exercise? It was alpha beta zk to the alpha, right? Plus beta times the expected value of v of pi kz z prime conditional on z. Well, our value function guess is A plus B times the log of K, but it's now K prime, right? It's next period's K, which would be what? Alpha beta zk to the alpha, right? Plus C times the log of Z prime, conditional on Z. You guys follow that? Okay, we've just scrolled forward our guess of the value function one period and substituted in our optimal policy function for K prime. Now we have something that we can match coefficients, right? Let's expand the terms here on the right-hand side so that we can do the match correctly. This first term, log of zk to the alpha minus alpha beta zk to the alpha, that to me looks like a log of 1 minus alpha beta plus a alpha times a log of k plus a log of z, right? You can break apart the log of a product. Plus, let's see, beta expected value of a, remember when the expected value of a sum is equal to the sum of the expected values, right? The integration has that property. So this is going to be beta times constant A, that's not random, plus beta times constant B times, what is this? That's the log of alpha beta plus alpha log K plus log Z. And then we're left with a beta times, now this last one is dependent on Z prime. So it's beta C times the expected value of the log of Z prime conditional on Z. So let me rewrite this by grouping the terms that depend on K, depend on Z, and then the terms that are constant. What are the terms that depend on K? You have an alpha log K plus a, let's see, beta B alpha log K. You have a log Z plus a beta B log Z. everything else is just a constant, right? Plus log of 1 minus alpha beta plus beta A plus beta B log of alpha beta plus beta C times the expected value of the log of Z prime conditional on Z. Here's why I want to make one additional note. Even though Z prime is a random variable, the expected value of Z prime conditional on Z is just some number, right? We know what the distribution of Z is, and so we can evaluate that expected value. It's just some number, and so it gets lumped into the intercept term in the value function. And so will show up in the constant A, but will not be part of B or C. Right? Now we can match coefficients, right? What must B be equal to? So this left-hand side B must be equal to the sum of the coefficients on the log K's on the right-hand side. So that's alpha plus beta B to the alpha. I'm sorry, beta B times alpha. So the unknown coefficient B then is just equal to, what is that? Alpha over 1 minus alpha beta. How about the coefficient C? What must it be equal to? C is equal to the sum of the coefficients on the log Z terms on the right-hand side. That looks to me like a 1 plus beta B, where B is equal to alpha over 1 minus alpha beta. So that's 1 plus alpha beta over 1 minus alpha beta, which means that C is equal to, let's see, 1 minus alpha beta plus alpha beta. That's a 1 over 1 minus alpha beta. Those are the two main slope terms in the value function. That gives us B and C. And you see they only depend here on alpha and beta. The intercept term is not as important and is going to be a little nastier, right? A would be equal to then the sum of all of these constants here. That's the log of 1 minus alpha beta plus beta A plus beta B times the log of alpha beta. Well, B is equal to alpha over 1 minus alpha beta. So that's alpha beta over 1 minus alpha beta times the log of alpha beta plus beta times C. Well, that's beta over 1 minus alpha beta times the expected value of the log of Z prime conditional on Z. This can be solved. It's a linear equation in A. So A would be equal to 1 minus beta inverse times the log of 1 minus alpha beta plus alpha beta over 1 minus alpha beta times the log of alpha beta plus beta over 1 minus alpha beta times this conditional expectations term. And what's that equal to? We know the distribution of Z. That should just be equal to the sum from J is equal to 1 to N of Qij of log Zj. Assuming that, of course, this assumes here that Z is equal to Zi. It's just some number, right? That's the conditional expectation of the log of Z prime, given that you know that Z is equal to, let's say, Zi. So that takes the sum of all possible J's from 1 to N and weights them by their transition probabilities of the log of Zj. And so the intercept term and the value function depends not just on alpha and beta, but it also depends on essentially the stochastic, the parameters that govern the stochastic distribution of the Z's. That is primarily the transition matrix Q. and the realization of the shocks themselves. Okay, that is all I have today. So again, what we will pick up next Monday then is a discussion about the long-run behavior of the Brock Mirman model. We want to do the following. We want to prove that capital and consumption in this model are going to eventually converge regardless of what the initial state of capital is, not to some fixed steady state, but rather to an invariant limiting distribution. What was one of the main properties of the optimal growth model? That regardless of how much capital we start with, capital will converge monotonically to the steady state in the long run. In this model, capital is going to converge not to a steady state, but some invariant distribution in the long run. The object is to prove what the domain of that distribution is. Can we identify what the lower and upper bounds on what the capital stock can possibly converge to? And then can we do something to actually characterize that invariant distribution in the long run? That's a difficult task that's going to take most of the class. Once we do that, then I guess the last thing to do will be to verify that the general form of the Brock Mirman model actually satisfies the transversality condition, right? Because in order to have identified an optimal solution to the problem, it needs to satisfy the transversality condition. So we need to verify that before we move on. I'm really hoping to finish that by the end of class on Monday, which means that on Wednesday, we should be able to start our discussion of search. It looks like I am, hold on, let me end this meeting.